Hello and welcome to the lecture on fundamentals of electric drives. In the last lecture, we were discussing about variable voltage and variable frequency control of induction motor. We will continue from that. Now, when we want to control the speed of an induction motor efficiently, we need to vary both. We need to vary the voltage as well as the frequency. Now, let us see the circuit diagram and the relevant equations. Now, what we have variable voltage and variable frequency control. The steady state equivalent circuit that we have already seen is still applicable here. So, we can draw the equivalent circuit of an induction motor. We start with the stator resistance, the stator leakage inductance, the rotor leakage inductance and the rotor resistance. Now, here this is R s, this is L s and this is L r prime referred from the primary side and this is R r prime by S. The applied voltage here is V here. Now, the current which is we have ignored the magnetizing reactance because that expression does not come direct in the torque equation. Now, the rotor current here is I r prime. So, this is our rotor current. Now, we can write down what is I r prime here. I r prime is V divided by under root the resistance square plus the reactance square. So, the reactance is 2 pi into F into the inductance L s L r prime whole square. Now, if we simplify this, we will get the following value R s plus R r prime by S whole square plus 4 pi square F square into L s plus L r prime square under root. Now, what we do here, we know that we have to find out the maximum torque and the maximum torque for the induction motor occurs for the following value of the slip. So, x max t is given as R r prime divided by this term can also be expressed in terms of the reactance. So, R r prime divided by under root R s square plus x s plus x r prime square, we have a plus and minus. So, this x s is the stator reactance which is 2 pi f into L s, x r is the rotor leakage reactance which is 2 pi f into L r prime. So, when we substitute this expression for the torque equation. So, what is the equation for the torque? Torque is given as 3 by omega m s into I r prime square R r by S. So, that is 3 by omega m s into V square divided by R s plus R r prime by S whole square. I am now writing in terms of the reactants plus X s plus X r prime square into R r prime by S. Now, what we do? We substitute in the torque equation the slip for the maximum torque. Now, we see that the slip for the maximum torque has two values, one is a positive value, other is a negative value. Positive value is for the motoring, negative value is for the braking condition or generating condition. So, when we substitute this x max t in this equation and simplify this, we get the expression for the maximum torque. So, T max is given as 3 by 2 omega m s into V square divided by R s. We have two values here plus minus under root R s square plus x s plus x r prime whole square. So, what we get here is the maximum torque. We know that induction motor will have maximum torque from the torque speed characteristic. The maximum torque depends upon the square of the voltage. We have seen here that T max is proportional to V square. Now, in this case again we replace this reactance by frequency. So, if we do that, what we get here is the following: 3 by 2 omega m s into V square divided by R s plus minus R s square plus 4 pi square f square into L s plus L r prime square. Now, we divide everything by f square. So, if we divide the numerator by f and the denominator f square and f square, we get the following equation. So, this is what we get here. T max is equal to some constant k into V by f square divided by R s by f plus minus R s by f whole square plus 4 pi square L s plus L r prime whole square. Now, let us just go back to our previous equation. In the previous equation, what we found is the following, that we have the expression for the maximum torque. What we do? We divide here by f. Okay. So, if we divide this by f here, we get f here, and we divide the numerator, the denominator also by f. So, we divide by f. Now, when the value goes inside the square root, this becomes f square. So, this by f square, this also by f square. So, we have some cancellation here, this f square will be cancelled with f square, and this is r by f whole square here, and this omega m s is a function of the frequency. What is this omega m s? Omega m s is the synchronous speed, that is equal to 2 pi f divided by p by 2. So, it means the synchronous speed is also a function of frequency. So, one more frequency term will be coming from this omega m s. So, this will make it v by f square, and we have some constant here. So, what we get finally is the equation that we wrote here, that v by f square, some constant k which depends upon the number of poles, factor of 3 and so on, and in the denominator we have r s by f, plus is for the motoring action and minus is for the generating action, under root r s by f square plus 4 pi square Ls plus Lr prime whole square. Now, we got the expression for the maximum torque. Now, usually the frequency is high. When we are talking about a 3-phase induction motor, let us say the normal frequency or the rated frequency is 50 hertz. So, when you operate at 50 hertz, f is a large value. We can vary the frequency, but if the frequency is on the higher side, we can ignore Rs by f with respect to the reactive part. So, in this case, for higher value of frequency, f, what we can say here is the following. We can say that Rs divided by f is much smaller compared to 2 pi Ls plus Lr prime. F is large. So, since we have a large value of f, so we can say that Rs by f is much smaller than 2 pi Ls plus Lr prime. So, in the denominator we can ignore these terms. We can in fact ignore this term because f is a large value, resistance is usually small because of the copper winding. We can also ignore this part. So, what we get finally by ignoring Rs by f, we get the following equation. So, T max is equal to some constant k V by f square divided by 4 pi square Ls plus Lr prime square under root. So, this is 2 pi into Ls plus Lr prime. Now, this is our equation which gives the maximum value of torque. Now, we now see that the maximum torque remains constant if V by f is kept constant. That is the reason why we always keep V by f constant when we are varying the voltage and the frequency. So, T max remains constant if V by f remains constant, and that is the reason why we keep this V by f constant, and this type of control is often called constant volt per Hertz control. This type of control is known as constant V by f control or constant volt per Hertz control. So, this is the reason why we have to keep the V by f constant, but we have ignored the stator resistance. Our assumption is that for higher value of frequency f, this can be neglected, Rs by f can be neglected. What about if the frequency is low? If the frequency is low, Rs by f can no longer be neglected. So, if the frequency is low, this part will dominate. So, to maintain the same torque, what we have to do? We have to increase V by f. So, V by f, although it is kept constant for higher value of frequency, V by f is increased for the lower value to account for the stator resistance drop. So, V by f is increased for lower frequency to account for stator resistance drop. So, let us try to see what is the characteristic that we have. Now, in one side we have the voltage, other side we have the frequency. So, we are keeping V by f constant. So, ideally we will be moving in a straight line passing through the origin, but however at low frequency we increase V by f to account for the stator resistance drop. So, this is our function that we have to follow. Now, given a frequency, we have to find out the corresponding voltage. So, if we are given a frequency, we can use this function value and find out the corresponding voltage. Now, when we reach the rated frequency, we also reach the rated voltage, because as we are increasing the frequency, the voltage is also increased. So, when we reach 50 hertz, the rated frequency, we also get the rated voltage. Thereafter, even if you increase the frequency, the voltage should not be increased, because a motor is designed for a given insulation. Now, if we apply, let us say 300 volt to a 230 volt motor, the insulation will be stressed. So, we should not be exceeding the voltage rating of the motor, and hence when we increase the frequency beyond the rated speed, voltage is maintained constant, only the frequency is increased. So, beyond the rated speed, rated frequency, this is f rated, we get V rated. After that, we do not increase the voltage. So, the voltage is maintained constant. So, this is the function graphically plotted here, and as we go on varying the frequency, we have to increase the voltage initially, and after the rated frequency, voltage is maintained constant. Now, this we have to implement when we realize V by constant V by f controlled induction motor drive. Let us see how we achieve this. Now, we go for an open loop control. Because we do not have to have the closed loop in this case. So, what we give here is the frequency command, which is fed to a delay block, and then this delay block gives the frequency reference. So, we have to find out the voltage also. The voltage is obtained from the function that we have just discussed. This is V by f function, V and f. So, we apply in this case the frequency here, and what we get output of this is the reference voltage. And this reference voltage and reference frequency is fed to a variable voltage and variable frequency inverter. So, we feed this to a variable voltage, variable frequency inverter. So, we have the DC input here, we have input DC voltage, and the inverter converts this DC voltage into an AC voltage. We have the induction motor here, it is a 3-phase induction motor, and the output of the inverter is 3-phase like this. And so, VF stands for variable voltage, variable frequency, and this is what is inverter. So, VF inverter here. Now, once we change the frequency, now when we are changing the frequency, it cannot be changed abruptly, because if we change the frequency abruptly, the machine may be unstable. So, it has to be changed slowly, that is why we have a delay block here. So, we have a delay block, because if we apply a step change of frequency here, actual change will be delayed like this. So, this will allow the machine inertia to respond, and as we are varying the frequency, this is our frequency command here, the voltage is also changed in accordance with this relationship. So, we maintain V by F constant in this case, excepting for the low speed or the low frequency region, where we increase V by F to account for the stator resistance drop. Now, this will ensure that the torque of the motor is constant. Now, if we draw the torque speed characteristic of this drive, we get the following nature. Our speed is in the y axis and torque is in the x axis, we have the origin here. So, this is the characteristic that we get. So, we go on getting this characteristic is for the motoring and for the regenerative braking. So, as you go on changing the frequency, we get all these parallel characteristic. The peak torque or the maximum torque remains the same. So, this is how the torque speed characteristic looks like. So, as you go on reducing the frequency by maintaining V by F constant, we get a family of curves which look like this. So, in the generating region also we get something like this, with peak torque almost remaining constant. So, this is the maximum torque. So, this maximum torque is almost constant here, T max, and this is the negative of the maximum torque. If we say this is T max 1, this is minus T max 2. So, this is for the braking or for the generating, because the torque is negative here, and this for the motoring. So, this is the family of curves when we go for a variable voltage and variable frequency control, maintaining V by F constant, we get the family of curves here. Now, this is the base speed, this is omega ms, the synchronous speed, the rated synchronous speed. Beyond that, we reduce V by F, we keep the voltage constant, but we increase the frequency. So, the V by F reduces, so that leads to reduction of the torque. So, gradually the torque reduces. As you go for the higher and higher speed, the torque will reduce, and this is represented by this characteristic. So, beyond the base speed, we get reduced torque. So, up to the base speed, what we do? We maintain the torque constant, but beyond the base speed, this is our base speed. Beyond the base speed, we go for variable torque or the reduced torque here, but the speed increases, but the torque decreases. So, this is called constant power mode or constant powering region. And before the base speed, what we get here is constant torque region. So, this is the torque speed characteristic of an induction motor when supplied from a variable voltage variable frequency inverter, and we maintain V by F constant up to the base speed. Beyond the base speed, voltage is kept constant, frequency is increased. So, the V by F decreases, and hence as per the equation, if you decrease V by F, torque reduces, and that is something like a constant power mode. So, now this is an open loop control. If we see here, this control is open loop, because there is no closed loop feedback here, and also we do not have any control over motor current. So, what are the drawbacks here? The drawbacks are the following. This is an open loop control, no direct control over the motor current, and stability may not be guaranteed in transient condition. So, we are only changing the frequency in the open loop and the voltage is changed in accordance with the frequency. We do not know what is the motor current. It may so happen that the motor is overloaded. It may be drawing a large current, but there is no clue we have to know whether it is loaded, overloaded or not. And furthermore, if we vary the frequency quickly, the motor may enter into unstable region. So, to avoid all these things, what we do is that we go for sleep frequency control. So, the sleep frequency control is a better control compared to open loop V by F control. So, we will be discussing next about the sleep frequency control. This is called sleep frequency or sleep speed control. Of induction motor. Now, why should we go for the sleep frequency control? Now, let us understand the philosophy behind sleep frequency or sleep speed control. What is sleep speed? Now, if we draw the torque speed characteristic of an induction motor, we get the following curve. This is the torque speed characteristic, speed in the y axis and torque in the x axis, and this is the synchronous speed. Here the sleep is equal to 0, here the sleep is equal to 1, it is the origin in this case, and speed is in the y axis, torque is in the x axis. Now, if the motor operates at certain value of speed, say for example, this is the speed at which it is operating. So, this is omega m, let us say this is omega m. So, what is sleep speed? Sleep speed is given as the differential speed between the synchronous speed minus omega m. Now, usually if you take a constant torque load, if we take a constant torque load here, this is our T L. Now, this region is so called the conventional stable region. This is the stable region for constant torque load, and here we get the maximum torque T max. So, this region is so called the stable region, and this region is called the unstable region. Stable and unstable is defined with respect to a torque profile. For a constant torque load, this region is a stable region, this region is an unstable region. So, if we have a torque which is little higher than that, and we see that it intersect the torque speed characteristic in 2 points, one is at this point, other is at this point. So, for a constant torque load, the point A is stable, this is a stable point, and point B is an unstable point. So, we have to operate the motor in a stable region. So, that can be ensured by controlling the slip speed, because slip speed is the difference between the synchronous speed and the motor speed. So, if we control this slip speed, we can always operate the motor within this maximum value of slip speed, which is omega S L max. And that is the main reason why we want to go for slip speed control or slip frequency control. So, the slip frequency control will ensure stability of the induction motor drive. So, we stop here for today's lecture. In the next lecture, we will be discussing more about the slip frequency control.